So let's begin our discussion about continuous random variables now. Okay, we've been talking a lot about discrete, where data moves in jumps. Continuous, you've got a range of possibilities, and anything inside that range is theoretically possible. Okay, so I need to explain something. In the continuous random variable, the less than or equal to sign is actually the same as the less than sign. The greater than or equal to sign is actually the same as the greater than sign. Really, the equal sign, the probability of anything happening exactly is actually it's zero chance that happens. It's kind of confusing. So here, let's imagine the number line in between 0 and 1. There are an infinite number of numbers in between here. Okay, so I'm just going to bend it like it's a clock. We've got some definite issues here, but if you think about this as modulus, you can just keep on counting. This point is actually 0 and 1, depending on how you define it. Okay, so it's like a clock. So here you've got some points that you are very understood. So the question is, what's the probability of x being exactly 0.25? What's the probability this arrow is pointing exactly at 0.25? And the answer is 0, actually. To ever exactly be on 0.25 is impossible. Imagine this, if you think that if the arrow is pointing exactly at this point, just imagine zooming in. And it'll either be slightly above it or slightly below it. Okay, if you still think that it actually is exactly precisely on it, then just imagine zooming in. To some level, on a molecular level, at some point, you will see you are never actually exactly on there. The probability that you're actually exactly on there is actually approaching 0. Okay, so you zoom in, you're either getting 0.249999 or a few more nines or 9 repeater. Okay, this isn't actually possible, so that's why the less than or equal to sign is the same thing as the equal to sign, because the probability that x is actually equal to x, there's no chance that it actually happens. Okay, so that effectively eliminates the equal sign from our calculations. Okay, so whether you're putting in less than or equal to, this is the same thing as just less than. Okay, so then the probability density function, now the equal sign is relatively useless. All it gives us is just the equation of the shape, the function, if you will. So that's what the probability density function gives us. We now are going to talk about the CDF a lot more. Okay, when we're talking about continuous variables, instead of the probability density function, we are going to focus on the cumulative density function, the cumulative distribution function. Okay, so instead of using p's, we use p's for discrete. F is now for function instead of p for probability. So f, the probability that x is equal to x, or also called as just f of x, large f of x is capital F's, you'll notice, is the probability of x being less than or equal to x. Okay, so what I'm trying to say here is f of x can be written as p where x is less than x, which now we're subbing in f for p's. Okay, and really what's going on, so here's the picture. I don't know what the shape is, but whatever the distribution function is, it determines what the shape is. So here's a shape, or any equation you can imagine, really. Here, in between 0 and x, here this is the cumulative from 0 to x. Then f, little f, of x being less than or equal to x, so anything less than or equal to this point, can be written as capital f of x. This is the cumulative distribution function. This is the probability distribution function. How we calculate it, well, it depends on how your equation is defined. But it could be from negative infinity up to the point x. For this picture, I just go from 0 to the point x, because anywhere else, the probability density function does not exist. Okay, so from the low point to your point x. Okay, to get this area, we simply just integrate over the probability distribution function, and we get whatever that probability is. Okay, so we're going to use this information a lot.